Okay, we are recording. So, welcome back again, everyone. Picking up where we left off in Module 1, we're still talking about steps of the scientific method here on this slide, getting ready to pivot back to ways that you might use data analytics for data-driven strategic decision making. So here we have the scientific method. I'm going to jump right into an example that comes from the famous textbook by Stock and Watson. It's chapter 4, Stock and Watson's Introduction to Econometrics, where we're looking at a policy question that is near and dear to me because I am an economist, as are many of our data analytics folks here at UNA. This policy question is, what is the effect on standardized test scores? You could do anything you want here, but it's standardized test scores in this case, depending on the size of a class in a public school. So you might think back to your own experience in public schools and a small class where you got a lot of direct attention from an instructor, or a very, very large class where you felt like you were swallowed up by a crowd. At the university level, of course, this is a much bigger debate because we sometimes have very, very small classes that we struggle to offer if we only get 4 people to enroll. And then we have enormous lecture halls. I've seen as many as 900 people, not at the University of North Alabama, but I've seen as many as 900 people crammed into an auditorium for a lecture and an introduction to the principles of microeconomics. That's a lot. So, what is the effect on test scores if you're going to have a larger or smaller class size? And the student-teacher ratio is going to do some work as far as affecting outcomes. In the previous 2 videos, we were talking about some of the things you can do with data analytics, and we had this cute little list of 3 things: descriptive analytics, predictive analytics, and prescriptive analytics. So that hierarchy is still in play here. You might start off with descriptive analytics, just looking at the data and trying to understand what's going on. The next higher bar would be predictive analytics. If you can build a model using something like ordinary least squares, which we're going to get into in Module 2, is all about regression. Can you build a model that will accurately predict the outcomes based on some set of inputs? The third tier in that hierarchy would be prescriptive analytics. Can your model now be stretched to map back to the real world to tell you something about the causal effect of changes in one of the variables? And if it can, which again is a higher bar and something that we fuss about quite a lot in economics, that higher bar, if you can make a causal statement about the effect of a change in X on Y, can allow you to make policy decisions like this one here. You may want to mandate smaller class sizes, or you may want to mandate larger class sizes. So the ideal way to look at this, or one ideal way to look at this, would be using data to find out the answer to the question. And you could imagine to just come up with a theory, right? You could have a theory that more direct communication with the instructor should allow students in smaller classes to do better. That's a perfectly workable theory and something that many people would probably buy into. So we've got some data here from California. It's a classic test score data set, also provided by the publishers of the Stock and Watson textbook that I referenced a moment ago. 5th grade test scores, Stanford 9 achievement test, math and reading. Nice. The average score for each district. Ooh, interesting. All right, so we've already got average scores at the district level. The student-teacher ratio is the total number of students in the district divided by the total number of full-time equivalent teachers. Okay, so we've got the average student-teacher ratio at this district, and we've got the average outcome for the district in terms of this achievement test. You could look at some simple descriptive statistics and say, hey, the average student-teacher ratio is 19.6, which is not too bad for public schools. At the university level, you might want to see something lower than that. Famously, Yale is very proud of its 7-to-1 student-teacher ratio. Okay, but 19.6 in public schools for something like 5th grade is not that bad. The standard deviation is, notice, we've got the first 2 moments of the distribution here. On average, you could expect the student-teacher ratio in a district to be about 19.6. You're equally likely to be some number above that as you are to be some number below that if you draw a district randomly from this list. The standard deviation tells you about, on average, how far people are above or below that average. So it would be perfectly ordinary to see somebody in a district that was 1.9 students per teacher higher than the average, which in this case you would add the 1.9 to the 19.6 and you'd have that new upper level, and you could say one standard deviation below, this is how we're going to start to build confidence intervals. The average plus or minus some number of standard deviations. The percentiles over here are also very interesting. 10% of students are in schools with less than 17.3, which is pretty good. 25% are in schools with less than 18.6, 40% in schools less than equal to 19.3. The median is 19.7, which is only barely higher than the average student-teacher ratio, so we might be able to say something about whether this distribution is skewed, but the median and the mean look like they're about the same, which is fair enough. And then 90% of students are below something like 21.9, which of course means that 10% of students are in districts where the student-teacher ratio is above 21.9. which we might think about being the bad end of the distribution. Test scores average is something like 654. You can imagine that this is something like an ordinary SAT type that goes up to 800 or whatever it might be. The standard deviation here is a lot larger because, of course, these numbers are a lot larger, and it's not unusual to see somebody who would be in a district where the average test score is 19 above that total average test score across all of these schools. And then again, we've got percentiles that'll tell you how many people are below a certain number in each of these districts. 10% of these districts have average test scores above 679, which is pretty good. 10% of districts have average test scores which are below something like 630.4. Doesn't tell us anything about the relationship between test scores and the student-teacher ratio. The first thing you might want to think about is a scatter plot. Now, we did this the other day when we looked at the relationship between earnings and years of education, because we had this prior belief that more years of education should correlate to higher earnings. And yeah, I've still got it here. On average, I see this upward slope, so it looks like people with more years of education have higher earnings. We may have to look at this again. Well, here's a different scatter plot. It's the student-teacher ratio on the horizontal axis, look down here, and the test scores are on the vertical axis. So on average, you might look at this and say, it seems like it's got a bit of a downward slope to it. It looks like this right side of the distribution is a little bit lower than the left side of the distribution. Now, it doesn't look like a line. It doesn't look like a nice tube. It looks like a big diffuse blob, which tells me that there's a lot more going on in the average test scores for these districts than just the student-teacher ratio. It doesn't look like a totally deterministic outcome based on your student-teacher ratio. But we can come up with ways to quantify how much explanatory power the student-teacher ratio has, and in this case it does sort of look like there's a downward slope. So maybe the higher student-teacher ratio districts do have worse test scores. How would you test that? How would you start to build a data-driven way of answering that question? Okay, so think back to the previous paradigm of 3 things that we might want to do, and we can come up with 3 new things that will build a story. So we'll start with comparing average test scores in districts with low student-teacher ratios to those with high student-teacher ratios. Estimation. If you want to estimate the difference, we can estimate many things. We'll start off by estimating the average in one set versus the average in the other set. Notice the break between the population that we might want to study, which is probably all schools everywhere, or all schools in the state of California, or all schools that could ever possibly exist in the state of California, because we're imagining a universe where we can change the student-teacher ratio and actually affect the outcomes here. But the sample that we have is this set of schools in the state of California at this time. So the sample is going to have an average. That average is our best stand-in for whatever the population average is, whatever the all-time, long-run, every school everywhere relationship between the student-teacher ratio and these standardized test scores might be. Or if I just take the average, then that sample average student-teacher ratio is a stand-in for the population average student-teacher ratio. Hence we call it estimation, because I'm using the data combined with a simple formula that everybody knows, like add up the numbers and divide by how many there were to get the average. I'm using the data to come up with an estimate for some sort of a population property. Okay, easy enough. And the distance between two groups, the difference there, is an estimate of the difference that the population may have between two comparable groups. Test a hypothesis. Again, a hypothesis for statistical hypothesis testing is going to be a numeric representation of an idea that has meaning that I want to know whether that idea is true or not. Test the null hypothesis that the average test scores in the two types of districts, high student-teacher ratio, low student-teacher ratio, are the same. Okay, so we're going to test the null hypothesis that the difference between them is 0. There's no difference between the high STR and the low STR districts. Then estimate an interval. I can estimate, I can test hypotheses, and I can give some sort of a probabilistic statement about how big that difference could be. This is going to be the confidence interval. Confidence intervals will be based on some statement of how likely it is that the truth is in that interval, okay, which will tell you something about how wide that interval has to be. Trivially, I could say, you know, the difference between high and low STR districts is probably more than minus infinity and less than positive infinity. And I would be right 100% of the time, but we can do better than that. So I could come up with something that's a 95% chance that it's within a given range. And that's the standard. 95 is the typical number for people. Okay, so compare the average test scores in districts. This will answer a specific question. What is the difference in test scores between high and low student-teacher ratio districts in the population? Well, here's my estimate. That's my best guess. And of course, this is what, a positive statement or a normative statement? It's just a positive question, right? I can answer that easily using a number, and it doesn't require value judgments. It doesn't require me to then go and say that it should be higher or lower, which is sort of the ultimate step that you could try to stretch out of this. The next thing, hypothesis testing, will answer whether the test score in the two types of districts is the same. That comparison being a very important step towards deciding whether I think that higher or lower student-teacher ratios are important for students. And this last thing will answer a question like, how likely is it? What proportion of values of that difference between the high and low STR districts are plausible according to the data. So a bit more nuanced, but it allows us to make statements that have measures of confidence attached to them. So I can tell you how, I can make a statement and tell you how likely it is that that statement is right or wrong, which will tell you the risks associated with making a decision based on that statement. Very nice. So we start to build these things. We do some initial data analysis. We compare districts. This is very ad hoc. We make a decision and say 20 is right in the middle. So I go back to the scatter plot, student-teacher ratio of 20, right in the middle. Imagine drawing a big red line down the vertical middle of the screen and saying the folks on the left have low student-teacher ratios and the folks on the right have high student-teacher ratios. Easy enough. Break them into two groups and I'll see that the average test score in the small class sizes is 657.4 and the average test score in the large class sizes is 650.0. So far, this is entirely consistent with my prior belief that the smaller classes are going to do a little bit better. Okay, but how big is the difference? I see that the difference is 7.4, but I'm not sure if 7.4 on this test is a lot, and I'm not sure if 7.4 in data that varies as much as this data varies is a lot. So the first thing that comes to mind is maybe I should ask how much these data vary. And the standard deviation in each of these two groups is 19.4 in the small STR schools and 17.9 in the large STR schools. Interesting. Okay, so this difference of 7.4 between the two groups is considerably less than the standard deviation, but what is the appropriate measure of distance to tell me whether 7.4 away from one group being 7.4 away from the other group is far? Is that unlikely, or is that just normal variation in the data like you would see in any noisy data set? Here, I wouldn't call this a terrible data set. N is 238 in the small group and 182 in the large group. 400 observations is not that bad. So anytime you've got less than 100 observations, you might be concerned that you just don't have a lot of data and you're not going to have a lot of ability to make really confident statements. More data should be better in most contexts. But 400 is not the smallest number I've ever seen. So first, estimate the difference between the group means. Test the hypothesis that there is no difference, which is going to require a specific statement about how large 7.4 is here. And then we could build a confidence interval based on the same logic, which we're working towards. One of the ways of doing this. All right, so first, get the average in the small group, get the average in the large group. Everybody should know the formula for the average. You just take all the observations in the small group. Here's your sum, right? Add up all the observations in the small group and divide by how many there were, which we'll call n small. Add up all the observations in the large group and divide by how many there were, which we'll call n large, and you'll see that the difference is 7.4. Great. The standard deviation across both districts is 19.1. Okay. That 7.4, though, standard deviation, let me go back to this picture. Standard deviation is, if I take this group on the right and say that the average is about here, a typical observation is a certain distance above or below. And you can look at this entire group and say, all right, well, the middle of the group is somewhere in here, maybe around 660. I think we saw an average a moment ago. And is it reasonable to say that a typical observation is about 20 above that or 20 below that? Yeah, sure. Up to 680, I've still got tons of observations, and down to 640, I've still got tons of observations. That's my standard deviation. So when I see that the average is 7.4 higher in the small STR groups, can I make that comparison based on the regular standard deviation? Unfortunately, the answer is no, because the average isn't supposed to be up here like some of the data are, and down here like some of the data are. The average is supposed to be right smack in the middle. So that standard deviation, 19.1, we can stretch into something called a standard error, which is how far the average should be from the true population average. Again, looking at a distribution like this, a normal distribution is what we're going to need to use to make probabilistic statements about whether I could believe that 7.4 was a normal thing to see if there was no difference in the population. Most of the time, the data in a normal distribution is going to be within one standard deviation of the truth. Here I've got the truth labeled down here on the horizontal axis with just standard deviations from the mean. Okay, well, if the mean was 660, then lots of stuff should be in the middle close to 660 given by the height of the curve. 68.3% of the data would be within one standard deviation, which was 19 above or 19 below. 95.4% of the data would be within two standard deviations, and one of those magic numbers that everybody likes to remember, 1.96 standard deviations above or below the mean would be the cutoff to have exactly 95%, not 95.4, but 95% of the data, meaning only 5% of observations. 1 out of 20 observations would be more than 1.96 standard deviations above average or below average. Okay, that's for talking about the observations. We can stretch that into talking about where the average should be as well. But the average varies much less than the original data. How much? The variance of the average is the variance of the original data divided by n, and the standard deviation of the average is the original standard deviation divided by the square root of n. So 19.1 tells me how much the data varies, but when I talk about the averages being higher or lower in these samples, the standard deviation of the average relative to its sampling distribution, which means if I could collect many samples, If I could collect this data many times from parallel universes, I'd see different averages. The standard deviation of those would be 19.1 divided by the square root of n. Okay. Here, difference in means test. Very nice. Excel will do this. This is in the data analytics tool pack. There is a button that will do this for you. So you don't necessarily need to memorize the formula, but all it is the distance between those averages divided by how far they should be from each other. If we're following the normal distribution, then 68% of the time they would only be one standard deviation away from each other. It was a question of coming up with the right standard deviation to make that comparison. We need the standard error here. And the standard error of the difference between two means is given by this formula. So we may revisit that at another time. This standard error involves the standard deviation in the small set and the standard deviation in the large STR set, which are just given by formulas like these. Okay. Now, if it turns out that 95% of the time, go back to here, 95% of the time, the data is going to be within 1.96 standard deviations of the mean. And 95% of the time, those two sample averages will be within 1.96 standard errors of each other. Well, then I can come up with a confidence interval and say, you know, the difference between them should be within 1.96 standard errors of 0 95% of the time, if the truth is that there's no difference in the populations. And then I can see whether the numbers that I get from the data are consistent with that hypothesis that I just postulated, if the difference between them is 0 in the population. Right? So my hypothesis could be there's no difference between the low STR and high STR schools in terms of their test scores at the end of the day. But I get a sample, look at the difference, and see whether it's consistent with that hypothesis. All right. Based on this average minus that average divided by the standard error, which will tell me the original difference, 7.4, divided by how far that should be if I have a sample of a given size from data with a certain standard deviation. Okay, we'll be doing this all semester and we'll visit it a couple of different ways. The confidence interval, which we put together, is the same idea. Your estimate goes here. And then if you say the truth should be within 1.96 standard errors of my estimate, 95% of the time, because my estimate should be within 1.96 standard errors of the truth, 95% of the time, relying on the same reasoning, my confidence interval for anything I estimate is going to be the original estimate plus or minus 1.96 of the standard errors. This actually plays a dual role because we can do the hypothesis testing using this confidence interval. Look what I come up with. 7.4 was the average that I came up with for the difference, right? Average of the small group, average of the large group takes the difference. That's the average difference between these groups, 7.4. And the standard error, when I divide the standard deviation by n, following the formula we saw a moment ago, turns out to be 1.83. Okay, so my confidence interval is 7.4 plus or minus 1.96 standard errors, which is how much that number should have varied relative to the population. It gives me a lower bound of 3.8 and an upper bound of 11.0, which I can read as either of these statements. The confidence interval doesn't include 0. Interesting. That's a hypothesis test right there. Or I could say there's a 95% chance that the truth is in this range, which doesn't include 0 difference. Or I could take it to the logical conclusion and say my hypothesis that the difference was 0 is rejected at the 5% level of significance, meaning there's a 5% chance I'm wrong. Go back to the picture one more time. We're saying if the difference is 0, I would see something like 1 standard deviation above and 1 standard deviation below 68% of the time. If the difference was 0, I'd see something like 1.96 standard deviations above and 1.96 standard deviations below 95% of the time. Okay, How far are we from 0? Well, 7.4 minus the standard error, 1.96 times the standard error only goes to 3.8, which does not include 0. So in fact, 0 is too far away from 7.4 to be plausible. Our 95% confidence interval basically says there's a 95% chance that the truth is in this range. If your skeptical friend comes to you and says, I think the truth is 0, I don't think that the student-teacher ratio matters at all, you say, well, the data says there's a 95% chance that the truth is between 3.8 and 11.0, which means there's less than a 5% chance that it's something like 0. I can be 95% confident that your supposition is wrong and it's not 0, and leave that behind. The hypothesis that delta is 0 is rejected at the 5% level. There's less than a 5% chance I'm wrong. I don't think it's 0. I think there really is a difference between these schools. So, hypothesis testing is going to work on that logical framework. We'll do it many times until everybody is comfortable with it, but it's the same pieces each time. And everything in this class is going to be based on normal distributions. There are other ways of going about it that I should point out, but we're blazing a trail right through the middle at this stage and not so much picking up all of the extra ways that we could do things. All right, so next steps include what? Mechanics of estimation. We've already started with something like the sample average. That's easy. Take the numbers, add them up, and divide by how many there were. Mechanics of estimating things like the median are very simple as well. You could take the sample median by ordering observations smallest to largest, and that's going to be a pretty good estimate of the population median if there's a population that you're trying to study with the sample. Hypothesis testing is going to work the same way. You're going to have many different stories that you could study, and in each case there could be something that you could postulate as being an interesting number. I think the difference between these two groups is 0. Or some friend says, no, I think the people who have one more year of education earn $10,000 more. Okay, I could test any kind of a statement like that. And I can build confidence intervals, which don't test a specific number, but give me a range. Any number in this range is considered plausible at the 95% level of confidence. This is great. If your skeptical friend comes to you and says, I think the difference between these schools with low and high student-teacher ratios is actually going to be about 5 points on the standardized test, well, then what would happen? 5 points is within my 95% confidence range. I say, I think with a 95% certainty that it's between 3.8 and 11.0. You're saying it might be 5? That is consistent with what I found in the data. So I would not reject your hypothesis that it's 5. I would fail to reject your hypothesis that it is 5. That's different from accepting the hypothesis, right? So we have a reject the hypothesis and we have a fail to reject the hypothesis, where I say, I don't believe that it's exactly 5, but 5 is consistent with this data. It's not far enough away to disturb me. Great. Regression, looking at the slope of a line, is going to have the exact same conversation built into it. And then, of course, we have to do some theory. All right, so we'll have to do a little bit of real math as far as estimation, hypothesis testing, and confidence intervals. Then we're going to have to figure out how OLS works, which is going to require some happy, fun whiteboard time. But that's fine. So the probability framework here, we'll start with estimation, testing, confidence intervals. We should all be familiar with these terms when I talk about the population, when I talk about a random variable, some number that is drawn from a distribution. The moments of the distribution are simple things that do all of the work here. The mean is a moment, the variance is a moment, the standard deviation, covariance, and correlation are moments. Conditional distributions, a distribution based on some information that you can provide. There is a unconditional distribution of student-teacher ratios, right, here in this vertical axis. But if I tell you that a school has, on the horizontal axis, I should say, if I tell you that a school has a student-teacher ratio above 20, that tells you a lot, not only about the student-teacher ratio, but about the test scores, right? I have a different set of test scores, and so on and so forth. Okay. So the population is the group or collection of all entities of interest that you wish to study, in this case, school districts. We think of the population as being infinitely large in this class. There is a simple way to modify what we do here, changing that 1.96, for instance, to account for a finite population if you're sampling from a finite population. It's rare in practice to do that, so we won't go back to it, but it's something that if you master what we do here, you can look up and implement very easily. You will draw a sample, which is a set of observations pulled from the population, and that will be the little bit of data that you have in order to make big generalized statements about the nature of the universe. The random variable is a numerical summary of a random outcome, which could be many different things. In this case, it could be the students learn a lot or the students learn a little. Well, I need to turn that into a number so that I can analyze it. The random variable that we used here is the district average test scores, where the students sit down, take tests, and each district reports their average score. So a random variable is always numerical in the formal sense of how we use this terminology in statistics. Population distribution of y, the probabilities of different values of y that occur in the population. You saw a scatter plot, and you saw the relative frequency of points on the scatter plot to the left, to the right, further to the left, and further to the right. We saw a histogram in the previous video, and a histogram is a good shape that tells you there are more of these observations and there are more of those observations. Or in this case, there are more observations down here where I see that people have relatively low dollars per hour for their earnings, and there are fewer observations up here where I see that few people have relatively high dollars per hour for their earnings. The frequency of observations above $80 an hour in this old data set is quite low. The frequency of observations below $20 an hour in this old data set is quite high. And so there's a shape to it. If I want to represent that shape as a vertical height of a distribution curve, it's the same idea as what we had with the normal distribution here. The frequency of observations close to the truth should be high, and the frequency of observations that are very, very far away from the average should be low. Okay. We have many other ways that we can make statements about these. The probability of sets of these values. For instance, the probability that y is between 640 and 660. Well, you could count up the proportion of observations that fall into that bucket and tell me what it is and say, oh, it turns out that's actually 26% of the observations. Okay, well then there's about a 0.26 probability of being in that basket. That 0.26 from my sample is also a good estimate of the whatever it might be in the population, which is probably close to 0.26 probability of having a test score between 640 and 660. These guys are important. So what can we do with the mean, the variance, and the standard deviation? There is a bit of notation involved in talking about the mean that we will use. The average is, as you know, just take the sample observations, add them up, and divide by how many there were. You might get tired of writing that formula over and over with the big sigma and the yi and divide by. So instead of doing that every single time, I might talk about the expected value. The expected value in a population, the true average, the expected value of y, denoted by E of y. Great notation, saves a lot of time. For the population, that'll just be mu y. And then our sample estimate of that will be the sum of all the observations divided by n. Great. The variance, as it turns out, is the average of something a little bit different. You take the observation and you look at how far it is from the population average. Sometimes observations are higher, sometimes observations are lower, and in rare cases they could be very, very high or very, very low. This is not bad, but the variance is the average of that squared, which makes them all positive and makes it easy to sum. will tell you something about how far away people are from average, on average, which is fun to say. But the units of the variance may not be what you want because I have y minus mu y squared. Example, if the average American man is 5'9" tall, great, the average is 5'9". But if I say that on average people are as much as 3 inches taller or 3 inches shorter than that, well, now I start to think that there are a lot of people who are 6 feet tall or 5'6". The variance here will take someone who's 6 feet tall minus 5'9" and say that's 3 inches taller than average. Square it, it becomes 9 square inches. Okay, so in terms of variance, the average American would be 9 squared inches taller than average, which may not be a set of units that makes any sense to you. So instead of variance, we may often rely on the standard deviation, which is the square root of the variance, which brings everything back to regular numbers. So variance is defined thusly with the expectation, and it's the second moment of the data. The standard deviation is the square root of that, which is a bit more reasonable and the one we tend to use. Fair enough. We already talked a lot about standard deviation back a couple of slides ago. So here you can see two examples of distributions. I'll go ahead and may as well move the picture of me. You see two examples of distributions. The one that is over on the right, I think you will see, is quite a lot skinnier. So you should be able to identify which of these has high variance and which of these has low variance. I presume everybody knows the one on the left is fatter. That one's going to have higher variance, and the one on the right has low variance. It happens, in this case, that they are centered roughly at about the same spot. So I could easily have two distributions that have the exact same mean, but different variance. I'll give you a terrible example. All right, so suppose I'm enrolled in an MBA program and I want to know what the average salary of MBAs is. So I go to Google and I say, Google, tell me the average salary for MBA students. And Google is happy to oblige, and it says the average salary for an MBA graduate in 2023 was $128,997, including a bonus package. That's not bad at all, but that could mean many different things. Suppose that the average student earns $128,997. How much spread is there in this distribution? It doesn't say. I don't think Google is going to know how to tell me the standard deviation of the MBA salary. Some people could be making quite a lot more than that. Some people could be making quite a lot less than that. Or we might live in a universe where all of the numbers are very close and you could expect to earn very, very close to $128,997 when you earn your MBA. So the variation in the data is just as important. It's a second order concept, but it's just as important as knowing the average if you want to make a prediction and if you want to make any kind of probabilistic statement about what those numbers could look like. And as we saw a moment ago, you can't do hypothesis testing without it. So we need the variance. There is this famous duality between moving things around in crazy ways. This famous break between the sample variance and the population variance. Let me fix that a little bit better there. Okay, all right. So the population variance is, honest to goodness, take everybody in the population and follow the formula. Notice we had variance here denoted as how tall you are minus how tall the normal person is, the average person. Not normal, average person is, and square them. Okay, take the average of that. That will manifest itself in the formula as this. How tall a person is minus how tall the average person is, squared, and then divided by how many observations there were. Well, it turns out that in samples, sometimes you have a lot of tall people, and sometimes you have a lot of short people. In a sample where you have taller than average people, the average is also going to be taller than average, which means that the average is a little bit closer to the data than it should have been. In the sample where you have a lot of short people, the average is also going to be very short, which means that the average is closer to the data in your sample than it would have been. So if I use this formula in a sample as an estimate of the population variance, I usually get, again, there's a sampling distribution here. Depending on the sample, I usually get a number that is a little bit too small. And so the correction for that in a sample is to add up these numbers and divide by n minus 1. When we go back to Excel, I will point out that there are two different versions of the standard deviation function in Excel. There are two different versions of the variance function in Excel, depending on whether you want the standard deviation of a sample or a population. This is easy to deal with because the data that you're looking at is almost always a sample. It would be very interesting to have an example where the data that you're looking at is actually all of the data for the entire population of everyone you could ever possibly want to study. So in general, in Excel, we will only use the sample formula, but that's fair enough. The next thing we would do with that is come up with the standard deviation from the variance, and it's exactly the same thing. We do have a bifurcation in the notation here. Population variance is usually denoted with the Greek sigma, and sample variance is usually denoted with the Latin s. Now the Greek sigma that you see here is a Greek letter for s, lowercase. They're both s, but we tend to use the Greek letters for the things that we don't know, the esoteric things, and we tend to use the Latin letters for things that we do know. The standard deviation of the population would be the standard deviation of everyone in the country if I'm studying the average height of an American man. Well, I don't have time to go out and survey people or hold up a ruler and try to find out how tall everyone in the country is, so I'm not going to have a population standard deviation, but I could estimate it. And I could come up with varying levels of sophistication for how I do that, but the easiest thing to do would be to come up with a sample and measure that. So the Greek letter here is a thing that I'm never going to get, but the Latin character is a thing that I can do right now if I have some data and I want to throw it into Excel. Okay, other ideas about what a distribution might look like. The distribution is easy to view using something like a histogram in a sample. But populations look like many different things. Here I've got in the top and left. Believe it or not, that's the normal distribution again. It's the same distribution we were looking at a moment ago. Sorry. So skewness and kurtosis are higher moments that tell you something about whether it's got a longer tail on the right or how long the tails are in general. And when we go back to Excel and look at the data analytics toolpack, in the descriptive statistics, it will tell us those numbers as well. This number, skewness, is equal to 0, which means that this one is actually symmetric. Draw a vertical line down the center of this distribution, and you see that the right half looks exactly like the mirror image of the left half. If I make that a little bit wonky, so that the left tail is longer than the right tail, as it is here, draw a line down the middle of the picture and you'll see that the one on the left is a lot longer than the one on the right. That's negative skewness. It's skewed to the left where the negative numbers are. Fair enough. The one over here is skewed to the right. The tail on the right is longer than the tail on the left, so that's positive skewness. Kurtosis does something similar, but it doesn't care about the directions. It just cares about whether there are a lot of these big numbers way out away from the middle. So kurtosis for a normal distribution is equal to 3. Not very meaningful numbers. Happens to be 3. There is something very entertaining called excess kurtosis, which is defined as kurtosis minus 3. And it's amazing to me that somebody invented that and got people to use it because it's just kurtosis minus 3. So proof to you that you can be successful with minimal effort. But kurtosis of 3 here is what we see in a normal distribution. A little bit more kurtosis is going to give me a bit more of a peak in the center, and then fat tails out here. So you see that in the normal distribution, as it falls off, by the time I get to 3, we're right back down on the horizontal axis. There's almost nothing happening there. There are almost 0 observations happening above 3 standard deviations. Let me go all the way back to this big picture. All right, so 99.7% of observations are within 3 standard deviations of the center in a normal distribution. And by the time you get out to 4 sigma, these are extremely rare. Well, the other picture that I see here was not like that. It still looks like there's a healthy amount of stuff happening by the time I get down to -3 or -4. Okay, these last two, even though this one's skew left and this one's skew right, you can see that both of them have more kurtosis than the original normal distribution. They're both looking like things out here past 3 might be a bit more frequent than they were up here, where they essentially never happen. And last thing here, a histogram, as you could produce in Excel, could be skew right or left, and you'll see many examples of this. We also have classical examples of types of data that we would expect to see skewness in. So here's a picture that's skew left, but instead of this nice, beautiful, hypothetical population distribution where I just have a curve to tell me what it should look like, I've got it broken up into rectangles to tell me how many observations fall into each bin, which is my nice sample counterpart. So negative skewness here, the tail on the left is longer. This one looks to be about symmetric. The tail on the right and the tail on the left don't look any longer. I think I could draw a line down the middle and use a mirror. And then this one down here has a long tail on the right, where I seem to have some observations up here that are much, much larger than what we have at the mode. Okay, classic example of things that look like this in economics. Income, right? Many people making fairly typical income, and then just a small number of people who make extraordinary income. Hopefully, very few or no people making zero and negative income. There are many people who are not in the workforce, but I presume that most of the people who are working have positive income. So it's a long right tail and essentially no left tail. We shouldn't have people making negative income. Okay, one more picture of the normal distribution, and then we get into z-scores. The z-score is something I will pick up with in the next video and talk about Chebyshev. So we'll stop here for this one.